Welcome to your notes on Gauss-Jordan elimination. Make sure you've set up your paper. You've got your name, date, class period in the top right-hand corner. You've got your title, Gauss-Jordan elimination. And the goal of this set of notes is to be able to use Gauss-Jordan elimination to solve a system of equations with 3 or more variables. So Gauss-Jordan elimination, much like Gaussian elimination, used to solve a system of equations, especially when there's more than 2 variables. Those old techniques from Algebra 2 of substitution, elimination, graphing aren't as efficient when we have more than 2 variables. But Gaussian elimination required that back substitution step. What Gauss-Jordan elimination is going to do is it's going to eliminate the back substitution. So you're going to be able to just get the answer right off of the matrix without doing that extra algebra at the end. So this time, our goal is to get the matrix into what is called reduced row echelon form. So row echelon form was the Gaussian technique. In Gauss-Jordan, we're going for reduced row echelon form, which is abbreviated RREF. And so reduced row echelon form, this is going to be a 3 by 3 matrix, 3 columns and 3 rows. It's still going to have 1s on the main diagonal. But this time, there will be 0s everywhere else. Okay, remember before, these top values here that I'm putting the green dots by, those could be any number. Now, we're going to make them 0s. And what's going to happen is we're going to have 3 numbers over here in the last column. And those are going to be our solutions. So x will equal this first answer, y will equal the second answer, z will equal the third one, and there's no back substitution. You get to just look now in the last column and see your answer. So let's talk about the technique. How are you going to actually get your matrix into RREF? So this technique is called down the stairs, up the stairs. And what you want to do first is you want to start by getting a 1 in the first column, first row. And then you're going to get all of the 0s that go below it. Once you have that first column looking perfectly in RREF, then you're going to start in the middle of the next row. And then you're going to do the 0 below that. And then once you have that, you're going to go down a level again. So if you look here, if I imagine stairs here, we're going down these stairs. We did this column, then we did this column, then we did this column. Once you have the main diagonal and all the 0s below it, then you're going to start working back up the stairs. So here's the staircase, and now we're going to work up this step. Those look the same. We're going to work up that step, and then once you've gone up that step, then you'll go up this step until you're totally in reduced row echelon form. If you get a row that contains all 0s, and we'll talk about what to do with that, but if for some reason there's an entire row that has all 0s, it has no 1 in it, you will want to move that row to the bottom. And we'll talk here shortly about what that means. But if it were to happen, and maybe it happens in your top row, you just want to, as a final step before you're done, flip it down to the bottom row. This is what you do if you have 0s. If there's an all 0 row. Now when I'm talking about the all 0s, I just mean on the left side of your line. Okay, so what are the actual steps for Gauss-Jordan elimination? Very similar to the steps for Gaussian. First, you're going to write the system as an augmented matrix. Then, you're going to transform the matrix into reduced row echelon form. That's those 4 steps that we were just looking at. Remember, Gaussian, once you were in row echelon form, you had to do back substitution. You don't have to do that here. Once you're in reduced row echelon form, you're ready to identify the solution. Now, there are a couple different outcomes. First, you could have one unique solution. If you have one unique solution, you're going to see your 1s down your main diagonal, and you'll see all your 0s everywhere else. If that happens, the last column has your solutions, and they're going to go in the order of the variables. So if this column represented x, and then y, and then z, the top answer represents X, Y, Z. So we read left to right, and we read our answers going down in the same order. What if you have a row of all zeros? So there's a couple things that can happen. In this matrix, we have a row of all zeros, and we have 1 on the other side. So what that's implying is that 0x plus 0y plus 0z equals -1. And simplifying this, 0 times anything is 0, 0 times y is 0, 0 times z is 0. 0 plus 0 plus 0 is 0. So what that's really saying is that 0 equals -1. That's a false statement. That's a false statement. If you happen upon a solution that looks like that, that implies that there is no solution. There is no solution. Sometimes when you have a row of all zeros, do it different color. Sometimes when you have a row of all zeros, you also have a 0 on the right side. So that's saying that 0 equals 0. That is a true solution. When you have a true solution, it means that there are infinitely many solutions. If it happens, you're just going to let the last variable, z, equal another variable. And you can choose any letter here except for x, y, and z because that's already in the problem. And then you will use your back substitution. So if z equals some letter t, let's use a different letter from the example so you can really see this work. If z equals b for my favorite teacher, then doing back substitution, that line says that, not x, there's no x in that line, y plus z equals 3, and z equals b. So y, I'm going to subtract b from both sides, y equals 3 minus b, or you can write that as y equals -b plus 3, doesn't matter. Then, back substitute again, go to your first equation, your first row, which says 1x plus no y's minus 2z's equals 2. And again, replace z with that variable. So x minus 2b equals 2. Adding 2b to both sides, we see that x equals 2b plus 2. And you can see that here. They just used the variable t. We used b. So there are a couple more vocabulary words that you're going to need to know. Thinking about all the different solutions, this is what they're going to look like when they're graphed. So remember, we have x, y, and z. So we're graphing in 3 dimensions. Instead of graphing lines, we're graphing planes. If you have one solution, your 3 planes meet in one place. So this is an example of your unique solution. You have one unique solution. If you have infinitely many solutions, that means that your 3 planes meet at a line. Right? And there are infinite points on a line, so that line represents infinitely many solutions. I'm going to abbreviate infinitely, INF, and solutions, SOL apostrophe N. So infinitely many solutions. If you have no solution, there's a couple things that can be happening. You could have 3 parallel planes. Remember when we did lines, if you had parallel lines, they would never touch. Parallel planes have no intersection. So this is an example of no solution. Another example of no solution, you can have planes that intersect. But if you look at this last picture, only the blue and green plane intersect. At this point that I circled, this line that I circled, the red one's not there. Similarly, down here, we've got the blue and the red, but not the green. And then lastly, we've got the green and the red, but not the blue. And we don't have any place where all 3 meet at the same time. So even though 2 at a time meet, not all 3 meet. So that's going to be another example of no solution. There is some additional vocabulary that you are going to be tested on. So firstly, we can call a system either consistent or inconsistent. A consistent system has 1 or more solutions, whereas an inconsistent has less than 1 solution. There's only one choice that's less than 1, and that's 0. Now, there are two types of consistent systems. Because it says one or more. If you have exactly one solution, it's called an independent system. That happens when there's just one. And then we can see here in a picture, we're never going to have 2 or 3 solutions. Our choices are 1 or infinitely many. So if you have infinitely many, then that is called dependent. That's the word that you need to know, dependent. So there's 4 words on here: dependent, independent, consistent, and inconsistent. So I want to go back and I want to label these pictures. Let's look in the top left. I have one solution. So if I have one solution, I am consistent. And then what type of consistent? I'm an independent consistent. We say this system is independent and consistent. If I have infinitely many, I'm consistent because there's more than one, but I am dependent, consistent and dependent. And then these other ones have no solution. Those are just going to get labeled inconsistent. They don't get a second word. Inconsistent.